So in this section, we're going to talk about inverse functions, and we're going to use those as a way to define logarithms and inverse trig functions. So let's just start with kind of what we want an inverse function to be. So let's let D be some domain, and R, let's say, this is the domain, R is the range of a function, f. All right, so this means f inputs things from D, outputs things in R. So what we'd like an inverse function to be is something that undoes this function. So what we'll say is we want our inverse function to go the opposite. It's going to go from R to D. So notice this has, the inverse function has domain R and range D. And one other thing to note is this inverse on it is not 1 over f. So let's maybe put a little warning over here. F to the minus 1 is notation for an inverse function. It does not mean 1 over f. So that's an easy mistake to make, so make sure we keep that in mind. So what do we mean by that f inverse should undo f? Well, if we let, say, x be an element of the domain, we want, if I apply f to x, and then I apply f inverse to that, that should give me x back. So whatever f does to x, f inverse undoes it. And we also want, if, say, y is in R, then if f inverse is the inverse for f, then f should be the inverse for f inverse. So I should take f of f inverse of y. This should be y. So this is what we mean by the inverse function undoing the function f. So let's look at an example and see how this might work. So let's suppose, just with a concrete example with a number, suppose I have 2 is in my domain, and f of 2 is equal to 4. So then if f has an inverse, so we won't always have an inverse function, we'll see why in a minute. Well, we'd want f inverse, well, if it should undo 4, so I would say this should be equal to 2, because f inverse of f of 2 has to be equal to 2. And notice this here is 4. So let's think about what's happening with this graphically. So let's pick a particular function now. So let's suppose y equals f of x is equal to x squared. So let's look at a picture of this. So my graph looks something like this. So now note, for this graph, we do have the case that if I go here, say to 2, and I evaluate that, that does give me 4. So I do have f of 2 is equal to 4 in this case. The problem is, so we would want to say, oh, so if it's going to have an inverse, then f inverse of 4 should be equal to 2. But the problem is notice that if I go here, minus 2 is also maps to 4. So when I'm trying to decide where should my inverse function send 4, I can't tell. Should it send it to 2 or should it send it to minus 2? So we can't have an inverse function because remember, to be a function, every input can only have one output, and we want our input 4 to have 2 outputs, plus and minus 2. So that's our problem. So what we can note up here above is the issue came about because if I take any horizontal line up here like this, one that 4 works as well, it hits this in 2 points. So we refer to that as the horizontal line test. So if it passes the horizontal line test, it hits at only 1 point. So remember, the vertical line test tells whether something's a function or not. The horizontal line test, so this is passed if any horizontal line hits the graph in at most 1 spot. It might hit it at no spots. So if we look below, if you were below the x-axis, we would hit it in no spots. Above it, we hit it in 2, so that doesn't work. So if it passes the horizontal line test, we say f is, you can either say 1 to 1 or injective. Either way is fine. So if it passes the horizontal line test, then since every output only corresponds to 1 input, we can define an inverse function. And sometimes, if we look above here, if we restricted our domain, we could make our function 1 to 1. So now let's consider, well, let's still take y equals f of x to be x squared, but now let's say with domain d to be all of the x's bigger than or equal to 0. So if we do that, we throw away part of the graph from before. And now we're only looking at the part where x is bigger than or equal to 0, so solid dot at 0 there. And then this is my y equals x squared with domain d. And so if we look at this now, at any point, we only hit the graph at 1 spot. So for instance, if we're at 4 here, we know that 2 was sent to that, so my f inverse of 4 should be equal to 2. If I'm at 1, I know 1 was sent to that, so f inverse of 1 is equal to 1. So more generally, for this inverse function, I want this, whatever this is, this should be x. So note, I want f inverse of x squared to be equal to x. So this function, f inverse of x, should just be square root of x, because that would get rid of that x squared. So we found our first inverse function. We can think about how this works in terms of a graph, is that if, say, y equals f of x is injective, so it has an inverse function, and we have, say, we take a point f of a and say this maps to b, so that means the point a comma b is on the graph y equals f of x. So let's look at a picture. So this means if wherever my graph is, I'm not going to worry about filling the graph in, but if I come over here to A, and I come up to B, this is a point on the graph. So that means if I take A, I map it up to B. And so that means my inverse function, f inverse of B, should be equal to A. So the point B comma A is on the graph of y equals f inverse of x. So we're just switching the coordinates there. So what does that mean in terms of graphing the inverse function? Well, if I have, say, my graph, so this is y equals f of x, so I know any point here, a comma b, is going to flip over So let's draw say this is my line. So this is the line y equals x. So that has points on it, say like c comma c. Well, on the other side of this, I'd flip this over and I'd be up here, and this would be the point b comma a. So all I've done is I take each point and I flip it over on the other side of the axis, and so wherever it hits this y equals x line, they're going to be equal there. And so this is the line graph y equals f inverse of x. So to write that out, to graph f inverse of x, we flip y equals f of x over the line y equals x. So that's an easy way to graph an inverse function. So now that we've reviewed inverse functions a bit, we're going to use this knowledge to define our logarithm functions and our inverse trig functions. So let's start with logarithms. So let's recall we have our exponential functions. Let's set y equals f of x to be a to the x with a bigger than 0. So if we graph these, we saw these before, what the graph looks like depends upon whether we have exponential increasing, exponential growth, or exponential decay. And that depends on the size of a. So if we have exponential growth, it looks like this. So this is when a is bigger than 1. And we have exponential decay in the other case when it looks down like this. And this is when a is between 0 and 1. So we can see from this the main point is looking at these graphs, these both pass the horizontal line test. So the function y equals a of x passes the horizontal line test. So what does that tell us? Well, that tells us we have an inverse function. And since this inverse function comes up a lot, we give it a special name. So we write it as log base a of x. So that a goes with the a for the exponential. So what does this actually mean? Well, since this is the inverse function, this means if I look at log base a of x, this has to give me x back. And if I look at a to log base a of x, this has to give me f back. Okay, so this is the requirement that I have this, and this is the requirement that I have this. Okay. The other things we can note here is we know in either of these cases, so we have the domain of a to the x is all real numbers, and the range is all positive numbers. So the domain of the logarithm, remember this has to be the range of the original function, so this is 0 to infinity, and the range of the logarithm has to be whatever the domain of the exponential is, so it's going to be all real numbers. And we can also graph by thinking of flipping over. We think of flipping this, the exponential above, and we think of flipping it over the y equals x line. It's going to look something like this. So an exponential grows very fast. Conversely, a logarithm grows very slow. So a logarithm is going to look something like this. Now, hopefully you've seen logarithms before, so you probably remember some of the properties of logarithms. But let's go ahead and see how we go about and do this. So let's let, say, x and y be in the domain of the logarithm. Now, since those are in the domain of the logarithm, that means it's in the range. So maybe write that there. So this is equal to the range of a to the x. So that means we can write x is equal to a to the w and y is equal to a to the z for some values, for some w and z that are in the real numbers. So if we think about going back up to our graph here, no matter what we pick our value to be, as long as it's a positive number, there'll be some value here that maps to it. So if this is, say, our x value, or let's maybe say y, so it fits more with our picture. If this is my y value, then this would be my z value here. So we can use that to give our first property of logarithm. So if I take log base a of x times y, you might remember what this rule for this is already, but let's see why this is true. Well, I can rewrite this as a to the w, a to the z, and then we use properties of exponentials. This is w plus z. And now we know that log base a and the exponential of base a are inverse functions, so this just gives me y plus z left over. And then I know that w is log base a of a to the w, and z is log base a of a to the z, which is log base a of x plus log base a of y. So that gives our familiar property that we'll rewrite here again. So that's one of our fundamental properties of logarithms, and you just see it follows from the fact that the logarithm is the inverse function of the exponential, and that's one of the properties of the exponential. The same type of argument, which you might want to do on your own just to make sure you understand it, gives the log base a of x over y is log base a of x minus log base a of y. One other property we have is if I look at log base a of x raised to the y, this is log base a, and then I'm going to replace the x with a to the w, which is raised to the y now. Our properties of exponents says that this is the same as a to the wy, which we know since log a and the exponential a are inverse, this is w to the y, which we'll write as yw, just changing the order. And this is y log base a of a to the w, which is y log base a of x. So this tells me I can bring my exponents down. So just to write this out, so we have it in one spot. So that's another property of logarithms we like to have. So those are basic properties of logarithms we want. So one other important thing is if we have a happens to be e, which we defined in the exponentials is a particularly important base for exponents, we often write ln of x for log base e of x and call this the natural logarithm. So this comes up a lot in the sciences. So that's why it's typical to use ln of x instead of log base other bases. So let's go ahead and try a few examples to see how to work with logarithms. Refresh our memory on this. So let's solve the following for x. So for the first one, let's take 17x is equal to 2. And of course, we can use any base we want for this, so I'll give you a couple of ways to do this. So if I apply log base 17 to both sides, I have this equation. And now remember our properties from before is I can bring this x out front and write this as log base of 17 is equal to log base 17 of 2. And log base 17 of 17 is 1, so this just gives me x is equal to log base 17 of 2. Right, because you can think of, maybe as an aside over here, think of this as log 17 of 17 to the 1. And we know that log base a of a to the x is equal to x. So this is just equal to 1. So that's one way to solve it. Another way is we could use natural logarithms. So I could apply natural logarithms to both sides. And I would have this equation. And now I can bring that x out front just like before. And I can just divide by the natural log of 17. And those are the same answer. Different ways of getting it, but if you were to look at those answers, say, in a calculator, you get the same number out. So let's try another one of these. Solving for x. So let's look at 4 times 3 to the x is 7 times 5 to the x. And again, plenty of ways to do this. So what I'll do first is I'll divide both sides by 7. So I'll have 4 sevenths times 3 to the x is equal to 5 to the x. Divide both sides by 3 to the x, so I'll have 4 over 7 is equal to 5 to the x over 3 to the x. We can use properties of exponentials to write this as 5/3 raised to the x. And now I can take natural log of both sides, so I'll have natural log of 4 sevenths is equal to natural log of 5/3 to the x. I can bring that x down front, so I'll have this x natural log of 5/3. And then if I divide both sides by natural log of 5/3, I'll have natural log of 4 sevenths divided by natural log of 5/3. And then we can use our properties of logarithms, if we like, to break this up in the top and bottom. So we have, and certainly you don't have to do that last step. You could leave it as natural log of 4 over 7 divided by natural log of 5/3. That's perfectly fine. Okay, let's try a few more examples with logarithms. So let's write the function, say p of t equals 10 times 2 to the t in the form p of t equals p0 e to the kt. So this will come up pretty often if you want to switch into using the e as your base for your exponential. So notice what I want is I want 10 times 2t to be p0 e to the kt, which I can write as p0 e to the k raised to the t. So this is going to tell me I want my p0 to be 10. Just think of putting t equals 0 into both sides. So now I have 10 times 2t equals 10 e raised to the k to the t. So this tells me what I need is I need e to the k to be equal to 2. I can take natural logs of both sides, bring this k out front, Remember, natural log of e is equal to 1, so I should have k is equal to natural log of 2. So if I go back to the top and plug these things in, I have 10 e to the natural log of 2 times t. Okay, so now let's move on to a couple of word problem examples that have to do with logarithms. Okay, so we have the concentration of car exhaust fume, nitrous oxide, which is the symbol is NO2, in the air near a busy road as a function of the distance from the road. So the concentration decays exponentially at a continuous rate of 2.54% per meter as we move away from the road. And what we want to ask is at what distance from the road is the concentration half of what it is at the road. Okay, so the first thing to note here is since we're saying this decays exponentially, if we let P be the amount or the concentration of the nitrous oxide, we know this is P0, which is whatever the initial amount was, and we can write this as A to the T. You could use E to the KT as well if you like, but we'll use AT here. And we see that it drops off at a continuous rate of 2.54% per meter. So that means my A is going to be 1 minus 0.0254, which is 0.9746. So my function is P0, 0.9746 raised to the T, and the T is in meters. Yes, the T is in meters, and the P of T is the concentration. So that gives us our equation. Now we want to turn what we're asked into an equation. So we want T. So remember, T is not time here, it's a distance. So maybe we should use a different variable, but we'll stick with T. So I want whatever this is so that I have 1/2 of the concentration left. That's what we're asking for. So if we set this up, that means I want to solve 1/2 P0 is equal to P0, 0.9746 T. We can cancel the P0 from each side by dividing by P0, so then I have 1/2 is equal to 0.9746 raised to the T. I'll take natural logarithms of both sides. I can bring this T down front. And now I can divide through, so I get T is equal to natural log of 1/2 over natural log of 0.9746. And if I want to be a little bit slick with this, I can use the top is natural log of 1 minus natural log of 2. And natural log of 1 is equal to 0. So this is negative natural log of 2 over natural log of 0.9746. This is because natural log of 1 is equal to 0. And the way to see that is because of the inverse function. And so why is this? This is because e to the 0 is equal to 1. And so that means that t, if you want to plug this into your calculator, is approximately 26.94, and this is measured in meters. So just about 27 meters from the road, the concentration of the nitrous oxide will be half of what it was at the road. Let's try one more word problem with logarithms before we move on to inverse trig functions. Okay, so let's say we have a cup of coffee that contains 100 milligrams of caffeine, and the caffeine leaves the body at a continuous rate of 17% per hour. Okay, so we're going to have several parts to this. So first, let's write a formula. For the amount of caffeine in the body T hours after drinking that cup of coffee. So that's our first question. So to do this, again, we'll use P of t is equal to P0, let's say a to the t. In this case, I know P0 is 100 milligrams because that's the amount of caffeine in the cup of coffee. So when we first drink the cup of coffee, that's how much will be in there. And since I know it's decreasing at 17%, A is going to be 1 minus 0.17, which is 0.83. So my P of t, my formula is 100 0.87 t. Or sorry, 83 t. Now, the second thing is let's go ahead and graph this function. So for this, we know we have exponential decay. So it's going to start up here at 100. That's when we drink the coffee, and then it goes down. It shouldn't go down into the something like this. Something like that. And for the last things, let's find the half-life. So half-life of the caffeine. So remember, this is how long it takes for half of the caffeine to be removed from the body. So for this, we want 1/2 P0 is equal to P0 a to the t. That's our half-life equation. So for us, we have 1/2 100 equals 100 0.83 t. Cross off those 100s, and then take natural log of both sides. So remember, the left-hand side simplifies to negative natural log of 2, as we saw in the previous example. And this becomes t natural log of 0.83 divide through, and I get negative natural log of 2 over natural log of 0.83. And if we plug this into the calculator, this is about 5 hours. So about 4.98 hours is the half-life of our caffeine. Okay. So now let's move on to our inverse trig functions. So we saw above that a function has an inverse if and only if it passes the horizontal line test. As we can recall, our trig functions definitely don't pass a horizontal line test. Any horizontal line, for instance, if we look at sine x, any horizontal line is going to hit sine of x a lot of times if it happens to be between minus 1 and 1. So, for instance, if I take my sine function here, if I take a horizontal line, it's going to hit a lot of times. But what we can do is we can do the same idea as we did with the function y equals x squared, and we can restrict our domain of our trig function so that it does happen to be 1 to 1 on the domain. So we can start here, look at minus pi over 2, start here, it's going to go up until you get to pi over 2, and notice it is 1 to 1 on this part. So we restrict to that domain. So if we restrict to the domain minus pi over 2 to pi over 2, then it is injective on that domain. So it has an inverse function. Now this does depend upon this choice of going from minus 1/2 or minus pi over 2 to pi over 2. You could pick a different domain where it's injective and you'd have a different inverse function then. So you do have to be a little bit careful of that. In this case, that sometimes you might be asked, well, what values of theta is, say, sine of theta equals pi over 4? Well, you have to be careful because there's going to be infinitely many of those. In this inverse function, if you apply that, would only give you one value. So you do have to take some caution here. So we denote the inverse function by, some people will write it as arc sine of x or sine inverse of x. And a lot of times the reason you use the capital S on the sign instead of the lowercase when we're doing the inverse is to make sure the reader or the user understands that it's only inverse for this particular domain and not overall. So we see the domain of, say, inverse sine. Well, the domain should be the range of sines. This is going to be from minus 1 to 1, and the range is going to be, well, what is the domain of sine? So minus pi over 2 to pi over 2. And we can graph this by looking at this, a graph here for y equals sine of x, with the restricted domain, and we know that we're going to flip over y equals x to get this. So what we'll end up with is, well, we want to go from minus 1 to 1, and from pi over 2 to, say, minus pi over 2. And then our graph, if we flip it over that axis, is going to look something like this. So it's an increasing function that we got by just flipping over the y equals x line. Now we can play the same game with cosine and tangent. So let's do that. So if we start with cosine, again, this is going to horribly fail the horizontal line test if we were to just graph the whole function. All right, so it's a very bad picture of cosine, but if so, we'd see it fail all of these spots. So we're going to do the same thing we did for sine. We're just going to restrict what parts we're looking at. And so for this one, we're going to start here, up here at 1, and we're going to look at the part that goes down until we get to here. So this is at pi, that's at pi over 2. So we restrict to that part. So this one has a domain of 0 to pi and a range of -1 to 1. So we have an inverse cosine. Again, just this restricted cosine over here. And so we'll often call this arc cosine or cosine inverse of x. And so this will have a domain of -1 to 1, just like to match the range of our cosine, and range 0 to pi. And if we want to graph this, again, we're just flipping over the x-axis. In this case, we're going to have 1, -1. We're going to go up here to pi. The graph's going to look something like this. And this here is at pi over 2. Not the best picture, but get the idea. It should be going at that point there. And finally, the last one we'll look at is arctangent. So if we look, so now for tangent, if we remember what the graph of tangent looked like, we had all of these asymptotes where cosine was 0, so we draw all these in. So this was minus pi over 2, and so on. And our tangent looks something like this, and it fills in each of these spots looking the same, just shifted. So again, this very badly fails the horizontal line test, but again, we can restrict our domain just like before, and we'll just look at the part here between minus pi over 2 and pi over 2. And now if I draw my tangent just for this restricted domain, it looks like this. And we can see here this does pass the horizontal line test. So our inverse function in this case, we'll write this as arc tan x, or tan inverse of x. Now notice up here, for my restricted tangent, this has domain minus pi over 2 to pi over 2. And notice we don't include minus pi over 2 or pi over 2 because of the asymptotes. And the range here is all real numbers. So down here, my domain is going to be all real numbers, and my range is going to be minus pi over 2 to pi over 2. And when we graph this one, we're going to put in those asymptotes, and now they're going to be on this axis, pi over 2 minus pi over 2. And my function is going to look like this. Come up, go through 0, and go this direction. So this is my arctangent function. Okay. And you can read off the values of these functions by just remembering that they're inverse functions. So for instance, if I want, say, arctangent of 1, remember we're asking, so this is equal to theta. We want theta so that tangent of theta is equal to 1. And so we want theta equals pi over 4. And we want to remember it has to be in our, there's going to be lots of values of theta where tangent of theta is 1, but it needs to be in the range of our tangent, and since our arctangent, since our tangent goes between minus pi over 2 and pi over 2, it's only going to be pi over 4. So arctangent of 1 equals pi over 4. And similarly, we could say, okay, well, what's cosine inverse of, say, square root of 3 over 2? Well, we want cosine of theta to be square root of 3 over 2. And if we remember, that's when theta is equal to pi over 6. So on our unit circle here, it's this angle here. And of course, we could go any 2 pi over this. So it would also be pi over 6 plus 2 pi. So this would be, so this is 12 pi over 6. This would also be 13 pi over 6. But we only want theta in the range of arc cosine of theta, or arc cosine of x. And we see the range of arc cosine, remember, was from 0 to pi. So this 13 pi over 6 is too big. So we want this pi over 6. So this should be pi over 6. So that's how we figure out the values of the inverse trig functions. You have to be pretty familiar with your values of your trig functions to be able to do this. And then we just have to be very careful that they're actually in the range of our inverse trig functions.